Hello and welcome back. Let's look at time series data and how we actually analyze them and identify components of the data set. Right? So, essentially, a time series data set is a data set having some variable y changing over time t. So, for it to be a valid time series data set, so as I had said earlier, the variable y can be anything. It can be stock price, the price of a commodity, it can be number of passengers traveling, number of users coming to an e-commerce site. It can be any variable which is changing over time t. So, the x-axis is always time t. For it to be a valid time series data set, there are some requirements that the data set has to meet. The first requirement is that there must be at least 50 data points. If you have less than 50 data points, that means there are 50 different points in time at which the value of the variable y must be known. Right? For example, if there is one data element per day, then you need 50 days data. If it is once per week, maybe you need 1 year of data, and so on. The second requirement is often difficult to meet. It says the time intervals must be equally spaced. Right? So, this, for example, was difficult to satisfy in the first example of our time series data sets, namely the petrol prices in the city of Bangalore, because the people who had recorded the petrol prices on that website had done it roughly twice a month. It was not exactly on the 15th of the month and the 1st of the month or something like that. So, then the question is, what do we do? Right? So, how do we adjust the time intervals so that they are equally spaced? If this requirement is not met, most of the time series packages and their functionality will not work. It will simply say this is not time series data. So, you have to do some appropriate cleaning up, like do an interpolation or something, adjust the variable values meaningfully so that you get values on equally spaced time intervals. The third requirement is there must be no missing data points. Right? For example, if I am looking at rainfall data and there is rainfall data recorded every day, but some days the readings were not taken. Now, how do we indicate that? If the value there is 0, does 0 mean there was no rainfall or the data was not collected? Both are possible. So, in practice we run into such situations. But again, if there are missing data points in your data set, you have to do something meaningful, like interpolate between the previous and the next data time point to arrive at a reasonable value for that. Because if there are missing data points, the time series packages will not do their job. They will say this is not valid. Then there is a fourth requirement saying that the data set should be stationary. Right? There is a statistical property called stationarity, and it must satisfy that. One way to say that is it must have no trend, no seasonality, and no change in frequency or amplitude of noise. Right? So, this is very technical, we will get back to it a bit later, but if there is none of these, then the data is not very interesting. Right? So, essentially what happens in practice is we remove the trend, we remove the seasonality, or in other words, I will show you how we subtract those, and the remaining data must have the same frequency and amplitude of noise across the entire data set. In other words, its statistical distribution properties must not change over time. Right? And some of the examples we looked at satisfied this, some did not. Right? So, for a data set to be a valid time series data set, it must satisfy all these four properties: minimum 50 data points, equally spaced time intervals, no missing data elements, and stationarity. Then it is a valid time series data set, and we can go about doing analysis of that. So, I'm pretty sure you are familiar with the concepts of frequency and period. Frequency indicates how many times a particular event occurs in a given period or given unit of time. For example, if something happens 4 times a year, say a company like Infosys announces its financial results 4 times a year, every quarter. That then you can say its frequency is 4 times per year. If you invert that, you get the period. So if frequency is 4, then the period is 3 months. So if they announce the results every quarter, then the frequency is 4 times a year and the period is once in 3 months. Right? There is a particular period that we are usually interested in, and that is the period of 1 year. Right? So if there is things changing in a regular pattern over a period of 1 year, we call that seasonality instead of periodicity, because the seasons are changing, they come back every year. In fact, the year in the calendar is defined to match the seasonal changes that we experience on this planet. So if the period is 1 year, we call it seasonality, otherwise we call it periodicity. So if something happens once a week, we call it periodic. Right? So Sunday comes once a week, that's a periodic event. Summer comes once a year, that's a seasonal event. Right? In long-term cyclic variations are also possible. Right? We will look at some of that a little later. Now you can do the analysis in time domain or frequency domain. Right? So I think people who have studied electronics engineering will be especially familiar with this. Right? So for example, in the time domain, I can ask at what points in time did an event occur and at what amplitude, or what was the value of that variable y. For example, the southwest monsoon occurs in the months of June to September. So that is in the time domain. In the frequency domain, we look at not the time points but the frequency of occurrence of events. Right? So southwest monsoon has a periodicity of 1 year and a frequency of 1. So it occurs once in every year. Let us look at another data set, a very famous data set. This has sort of ideal properties. Some of these data sets are used to teach time series analysis because they're almost perfect for illustrating time series analysis methods. So this particular data set is also available in your R package. It is the data about how atmospheric carbon dioxide levels have changed in the last 60 years. From 1960 to the present time, how the CO2 level in the atmosphere has changed. And this is not talking about urban pollution levels. This is not in Delhi or Mumbai or Bengaluru. This is recorded in a very remote island in the Hawaii region called the Mauna Loa Observatory. So there is no really industrial pollution or anything else that has changed in that area compared to urban areas. But you will see that CO2 levels have been increasing. Now, consistently in the last 60 years, carbon dioxide levels in the atmosphere have increased, but they have increased from 320 to about 400 ppm, parts per million. Again, this may be misleading because of the way it is shown. The y-axis is not from 0, it is from 320. Right? Now, you will see that the black line in this graph shows what we call the trend. Right? That is, after you take out seasonal variations, year on year, how is it changing? So it is almost monotonically increasing, but it is not a perfect straight line. So why it is happening that way, that is for the atmospheric scientists and others to explain. But the red line is the actual data. So there is a very clear seasonal variation. There is more CO2 in some seasons and less in some other seasons. This may be because of the wind patterns and whatever else. But the seasonal variation is almost perfect in this data set. And if you remove that seasonal variation, you get the black line, which we call the trend. So there is a trend component and a seasonal component in this CO2 data set. If you take some other signal, right, this one is again from your textbook. It is some furnace exhaust gas data, and here you don't see any such clean pattern, right? So this is probably, the timeline is also probably in seconds or minutes or whatever, and you will see that it is not so systematic. So real data may be more like this than that perfect data that we saw over there. And the trend may be non-linear. Here is an example. The cost of making telephone calls in the US, right? So it used to be very expensive. For example, a call from US to India used to cost about $3.80 per minute, say a few decades ago. Now it has come down to almost zero. So you will see that the cost per minute of making a call, long distance phone call, has dropped exponentially, right? It has decayed so much, but in between there have been periods where it has increased again. Why it is so, you have to analyze, right? Now this is similar to our Olympic data set, but there's something interesting about this, right? If you, instead of plotting this on the normal scale, if you see the smaller graph in the inset, there the cost is plotted in a logarithmic scale, and in the logarithmic scale it becomes almost a perfect straight line, right? So in analyzing some data set like this, you don't need all of the special methods of time series analysis. If you just do a little math, plot it on a log scale, then linear regression on that log value will give you a perfectly good fit, and regression itself is a good technique to analyze this, to do any prediction and so on. You don't really need anything more sophisticated. So it doesn't mean that you should always apply time series methods. Sometimes there are easier ways of doing things. Let's look at something called non-stationarity, right, after a short break.